Here's a question. You've got two sorted lists of numbers, and you want the median, the value sitting right in the middle. Say one list is just 1 and 3, the other is just 2. Together that's 1, 2, 3. The middle is 2. Let's look at a small case. 1 and 2 in the first list, 3 and 4 in the second. Merge them in your head. 1, 2, 3, 4. 4 numbers, so no single one sits in the middle. When the count is even, the median is the average of the two middle values. 2 and 3 give 2.5. When the count is odd, it's simpler. There's exactly one middle value, and that's the median. One more rule. For even totals we return a decimal, the average of the two middle numbers. And here's the catch. The problem demands logarithmic time, O of log out plus n. As the lists grow huge, our work must barely grow. Okay, try the obvious thing first. What would you do by hand to find the median of two sorted lists? You'd merge the two sorted lists into one big sorted list, then walk to the middle. Simple enough. Let's do it. First list is 1, 3, 8, 9, 15. Second is 7, 11, 18, 19, 21, 25. Walk both lists at once, always picking the smaller front value. 1, then 3, then 7, then 8, and so on. You end up with one combined list of 11 numbers, fully sorted from smallest to largest. 11 is odd, so the median is the sixth value. Count in from the start, that's 11. It works. So what's wrong with it? Nothing for small lists. Watch what happens as they grow. To find one middle value, we built and sorted every single element. We touched all of them. If each list held 1,000,000 numbers, we do 2,000,000 steps just to grab the one in the center. That's linear work, O of m plan. The problem asked for O of log m plus n. We need to look at far fewer numbers. Let's slow down. Look at what the merge throws away. We carefully ordered all 11 numbers, but we only needed the one in the middle. The rest was wasted effort. Here's the real question. What does the median actually tell us about how the numbers are split? The median is the point where the numbers divide into a smaller half and a larger half. Equal-sized halves when the total's even, otherwise the left half gets one extra. So forget merging. What if we just drew a dividing line through each array, a left part and a right part? 11 numbers total. We want 6 on the left, 5 on the right. That left count never changes. Here's the move. If we cut the first array, the cut in the second is forced. Both left parts together must add up to 6. So we only choose one thing, where to cut the smaller array. The other cut follows automatically. When is a cut correct? Every number on the left must be less than or equal to every number on the right. Because both arrays are sorted, we only check the 4 numbers touching the cut lines, the two ends of the left, the two starts of the right. The test is simple. The first array's left edge must not exceed the second array's right edge, and the other way around too. And to find the right cut, we don't try every spot. We binary search, like guessing a number while halving the range each time. Watch out for one trap. You might pick the bigger array to search. Don't. Cut the smaller one, or its forced cut can fall off the edge. And when a cut sits at the very start or end, there's no number there. We treat a missing left edge as negative infinity, a missing right edge as positive infinity. Let's trace it. First list 1, 3, 8, 9, 15. Second list 7, 11, 18, 19, 21, 25. 11 numbers total. The left half needs 6. We binary search the cuts of the smaller first array. The cut in the first array can be anywhere from 0 to 5. Start the search. Low is 0, high is 5. Midpoint of the search is cut position 2. That puts 2 numbers from the first array on the left, so the second gives 4. Now the 4 border numbers. First array, left edge 3, right edge 8. Second array, left edge 19, right edge 21. Check 1. Is the first array's left edge 3 less than or equal to the second's right edge 21? Yes. Check 2. Is the second array's left edge 19 less than or equal to the first's right edge 8? No. 19 is way too big. So this cut is wrong. The second array put too many numbers on its left. We need more from the first array instead. Move the search to the right. Low becomes 3. Try again. New midpoint cut. Position 4. 4 numbers from the first array on the left, so the second gives just 2. Border numbers now. First array, left edge 9, right edge 15. Second array, left edge 11, right edge 18. Check 1. First array's left edge 9, less than or equal to the second's right edge 18, yes. Check 2. Second array's left edge 11, less than or equal to the first's right edge 15, yes. Both pass. This cut is valid. The left half holds the 6 smallest numbers, the right half the 5 largest. The total, 11, is odd. The median is the largest number on the left, the bigger of 9 and 11, which is 11. Let's run a second case, trickier. An even total, and a cut that falls right off the edge of an array. First list 1, 2. Second list 3, 4. 4 numbers total and even count. The left half needs 2 numbers. We search the cuts of the smaller first array, low 0, high 2. Midpoint cut. Position 1. 1 number from each array goes to the left. Borders. First array left edge 1, right edge 2. Second array left edge 3, right edge 4. The second check fails. The second's left edge 3 is bigger than the first's right edge 2. Move the search right. New cut. Position 2. Both numbers of the first array go left, the second array gives nothing to the left. Now the edge case. The first array's cut is at the end, so there's no right edge there. We treat it as positive infinity. And the second array's cut is at the very start, so no left edge. We treat that as negative infinity. Borders now, left edge 2, right edge infinity and negative infinity, right edge 3. Both checks pass. Even total this time, so the median averages the biggest left number, 2, and the smallest right number, 3. 2 and 3 average to 2.5. That matches the merged list 1, 2, 3, 4. Notice what we never did. We never merged the lists. Each guess threw away half the remaining cut positions, so a few guesses were enough. Each step halves the cuts, still worth considering, so the number of steps grows with the logarithm of the smaller array's length. And we only ever store a few border values, never a merged list. The memory stays constant no matter how big the inputs grow. Before you code, 3 things to keep in your head. First, always binary search the smaller array. The other cut follows from half equals m plus 1, divided by 2. Second, a cut is valid only when both crosses check out. Left of A less than or equal to right of B, A and D left of B less than or equal to right of A. One fails, you shift the search. Watch out for 2 traps. The cut lives between cells, never on one. Index means numbers on the left. And when a cut sits at the edge, use minus infinity or plus infinity for the missing side. Skip those guards and you'll crash on the smallest inputs. Okay, same logic in Python. Swap so A is the smaller array, work out the left half size, and set the search bounds on A's cut. Each loop pass picks a cut in A, and the cut in B follows automatically, since the left half size is fixed. Read the 4 border values. When a cut sits at an edge, fall back to negative or positive infinity. If both checks pass, the cut is valid. An odd total returns the largest left value. An even total averages the 2 middle ones. Otherwise, shift the search. If A's left edge is too big, go left. Otherwise, go right and try again. And that's the trick. Stop merging, start cutting. When a problem demands O of log n time, ask what you can throw away each step.